The moment that changed everything. Before there were stars, before Earth, before even atoms, there was a moment in time when the universe took its first major step toward becoming what we know today. A moment that occurred within just microseconds after the Big Bang. And from that point forward, everything changed at that time. The universe was an unimaginably hot soup of fundamental particles. No atoms, no protons, no neutrons, just pure energy and the tiniest building blocks of matter, colliding at mind-bending temperatures. Around 1/1,000,000th of a second after the Big Bang, that is 0.00001 seconds, the universe was still in its infancy. But already, it had reached a crucial milestone. This was when quarks and gluons, once freely roaming in a dense, high-energy plasma, began to slow down. The temperature of the universe was around 1,000,000,000,000 Kelvin. That is nearly 100,000 times hotter than the core of the sun. Under these extreme conditions, something miraculous began to happen. Quarks, the elementary particles that would one day form the heart of every atom, started combining into triplets, bound together by gluons, the particles that carry the strong nuclear force. These triplets formed the very first hadrons, protons, and neutrons. This event is not just a scientific detail. It is the foundation of everything. These particles, protons and neutrons, would become the basic bricks of all matter. From galaxies and stars to planets and people, everything we see today stems from this critical moment, and it all happened in less time than the blink of an eye. So how did this process unfold? Why were some quarks able to form protons and neutrons while others vanished into energy? And how did the rapidly cooling universe allow these particles to become stable? That is exactly what we are going to explore in the next part. From quark soup to particles, as the universe cooled past the 2 trillion Kelvin mark, something fundamental changed. The ultra-dense plasma of quarks and gluons, known as quark-gluon, plasma began to dissolve. Quarks could no longer move freely. They started binding together, locked by the strong nuclear force, mediated by gluons. These interactions are described by quantum chromodynamics, or QCD, the theory that governs how the strong force behaves at the tiniest scales. What emerged from this transition were hadrons, particles composed of 3 quarks. 2 major types of hadrons formed: protons and neutrons. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up and 2 down quarks. Though they differ by only 1 quark, that small difference would later define the structure of atoms, and by extension, the chemistry of the entire universe. But forming these hadrons was not a smooth process. It required just the right conditions. The universe had to cool enough for the strong force to trap quarks inside stable structures, but not so quickly that quarks would annihilate before forming anything, thanks to the rapid yet finely balanced expansion of the early universe. That delicate window of formation was just long enough. Protons and neutrons became the first long-lived particles in the cosmos. This transition marked a profound turning point. It was the moment when energy finally began to crystallize into matter, a shift from pure chaos to the first stable building blocks of the universe. And the story was only beginning. These particles now had to survive, interact, and prepare for the next transformation, becoming the nuclei of atoms. We will explore how that happened next. The balance between protons and neutrons. In the earliest microseconds after the Big Bang, the universe was a chaotic sea of particles constantly transforming into one another. Protons and neutrons, freshly formed from quarks, were no exception. At extremely high temperatures above 1,000,000,000 degrees Kelvin, protons and neutrons could freely interconvert through weak nuclear interactions. This transformation happened via a process called beta decay and its inverse, neutron-proton, plus electron plus antineutrino, because the energy was so intense. These reactions occurred rapidly in both directions. At this stage, the universe contained almost equal numbers of protons and neutrons, but that balance was fleeting. As the universe expanded, it also cooled. And as the temperature dropped below a critical threshold, the rate of these interconversions slowed. Eventually, The reactions became too sluggish to keep up with the expanding universe. Once it happened, the balance tipped. Free neutrons are unstable particles. They decay with a half-life of about 880 seconds, just under 15 minutes if they are not bound inside atomic nuclei. So as the universe cooled and these reactions ceased, neutrons began disappearing. Only the neutrons that managed to combine with protons in time would survive. The rest decayed into more protons and electrons. By the time the universe was ready for nucleosynthesis, the formation of atomic nuclei, the neutron to proton ratio had stabilized at roughly 1 neutron for every 6 protons. This ratio would prove crucial for determining the chemical makeup of the cosmos. Why? Because neutrons are essential for forming helium and other light elements. Without enough of them, the universe could never have produced the heavier building blocks of matter. In other words, a small difference in timing, a few seconds of delay or acceleration, could have led to a universe with a very different chemistry and perhaps no stars or life at all. Next, we will examine how protons and neutrons combine to form the very first atomic nuclei in a process known as primordial nucleosynthesis, the internal structure of protons and neutrons, and the role of beta interactions. To truly understand how matter formed after the Big Bang, we need to look deeper inside the particles themselves. Both protons and neutrons are not fundamental particles. Instead, they are made up of even smaller components known as quarks. These quarks are bound together by gluons, the carriers of the strong nuclear force. Within the framework of quantum chromodynamics, or QCD, a proton is made of 2 up quarks and 1 down quark. A neutron, on the other hand, contains 1 up quark and 2 down quarks. These differences in quark composition are responsible for the distinct properties of the 2 particles. For example, the proton carries a positive charge, while the neutron is electrically neutral. What makes this interesting in the context of the early universe is the role played by the weak nuclear force, one of the 4 fundamental forces of nature. Through weak interactions, quarks can change types of process known as flavor change. Specifically, an up quark can transform into a down quark, and vice versa. This transformation underlies beta decay, where a neutron decays into a proton, an electron, and an antineutrino. Conversely, a proton can become a neutron, given enough energy, by absorbing an electron and emitting a neutrino. These interactions were crucial in the first few seconds after the Big Bang. They allowed the universe to maintain a dynamic balance between protons and neutrons, as discussed in the previous section. But as the universe expanded and cooled, these interactions slowed down. Neutrons, no longer stabilized by rapid conversion, began to decay. Neutrons are inherently unstable unless they are bound inside a nucleus. Their average lifetime is about 880 seconds. That gave them a small window of time to bind with protons and form stable nuclei. If they didn't bind in time, they vanished, reducing the number of neutrons available for element formation. This delicate interplay between particle structure, fundamental forces, and decay rates determine the ingredients available for the next big transformation, the creation of the first elements. And that's where we turn next, the era of nucleosynthesis, the beginning of primordial nucleosynthesis. How the first atoms formed. Roughly 1 minute after the Big Bang, the universe had cooled to below 1 billion degrees Kelvin. This was a critical threshold. It meant that, for the first time, the building blocks of matter, protons and neutrons, could begin to bind together through nuclear fusion. This marked the start of a process known as Big Bang nucleosynthesis. The environment had to meet 3 strict conditions. The temperature had to drop below 1 billion Kelvin to allow stable nuclei to form. The density of particles needed to be high enough for frequent collisions. Time had to be just right, long enough for fusion to occur, but short enough to prevent particles from decaying before reacting. Here's what happened. The earliest reaction was the fusion of a proton and a neutron, producing a deuterium nucleus D, also called heavy hydrogen. This reaction also released a gamma photon, P+, and gives D plus gamma. Deuterium then served as the foundation for forming heavier atomic nuclei. It fused with another proton to form helium-3. D plus P gives He. To helium-3 nuclei could then combine to form helium-4. He plus He gives He. This chain of reactions occurred rapidly, within just a couple of minutes. Most of the available neutrons were locked into helium nuclei. By the end of the nucleosynthesis window, which lasted until about 3 minutes post-Big Bang, the universe had achieved a stable elemental composition, about 75% hydrogen, about 25% helium for trace amounts of deuterium, helium-3, and lithium-7. No heavier elements formed during this stage. The reason? The universe was cooling too fast. Fusion of elements beyond lithium requires multiple stages and stable environments, which only developed much later in stars. This phase laid the foundation for everything that followed. It created the raw chemical ingredients that would go on to form stars, galaxies, and eventually life itself. From a swirling plasma of high-energy particles, the cosmos had just begun to transform into a structured, element-rich universe. Why only light elements formed in the first minutes? A natural question arises at this point. If nuclear fusion had already begun, why did the universe stop at hydrogen and helium? Why weren't heavier elements like carbon, oxygen, or iron created during the Big Bang? The answer lies in the timing and the expansion rate of the early universe. During the first 3 minutes, the universe was expanding and cooling extremely rapidly. This fast expansion meant there was a very narrow window, only a few minutes, where temperatures and densities were high, enough to allow nuclear fusion to happen. Once the temperature dropped below about 100 million Kelvin, nuclear reactions slowed dramatically and effectively stopped. Another key reason involves the role of neutrons. Free neutrons are unstable and decay in about 880 seconds unless they are captured into a nucleus. Most available neutrons ended up being locked into helium for nuclei, a very stable and tightly bound configuration. Once those were formed, there were very few free neutrons left to build anything heavier. To build elements beyond helium like carbon or oxygen, you need triple alpha processes, where 3 helium nuclei fuse to form carbon, stable environments where high temperatures and pressures are maintained over long periods. But the early universe was not stable or long-lasting enough for these processes to occur. It cooled too quickly, and densities dropped too fast. There simply wasn't enough time. As a result, the Big Bang only produced the lightest elements, hydrogen, helium-4, tiny traces of deuterium, helium-3, and lithium-7. All heavier elements in the universe, carbon, nitrogen, oxygen, and so on, were forged much later in the hearts of stars through stellar nucleosynthesis. In essence, the Big Bang set the initial chemical conditions of the universe, creating a hydrogen-helium domina, tet cosmos. But it would take billions of years of stellar evolution for the rich diversity of elements we know today to emerge. Observational evidence from the universe. At this point, you might be wondering, how can scientists know with such confidence what happened in just the first few minutes after the Big Bang? How can they verify the primordial nucleosynthesis actually took place? The answer lies in observable evidence, specifically in the measured abundances of light elements throughout the universe today. This is one of the 3 main pillars supporting the standard Big Bang model. Alongside cosmic expansion and the cosmic microwave background, CM several space missions, such as WMAP Wilkinson Microwave Anisotropy Probe, Planck Satellite, European Space Agency Boomerang, balloon observations of millimetric extragalactic radiation, and geophysics, have measured the precise ratios of light elements like helium-4, which makes up about 25% of the visible matter in the universe, deuterium, helium-3, and lithium-7, which exist in trace amounts. These observed values align remarkably well with the theoretical predictions from Big Bang Nucleosynthesis (BBN). These predictions are based on factors such as baryon density, the universe's expansion rate, and its initial temperature. This match between observation and theory is a major success for modern cosmology. It proves that what we predict about the first minutes of the universe is not mere speculation, but a scientifically confirmed aspect of reality. In short, by analyzing the elemental makeup of the universe today, scientists have been able to look back in time, nearly 14 billion years, and confirm that the process of nuclear synthesis in the first 3 minutes of the universe really happened. The role of neutrinos and background energy, while protons and neutrons were forming into light elements. Another group of elusive particles was playing a crucial role behind the scenes: neutrinos. Neutrinos are nearly massless, electrically neutral particles that interact only via the weak nuclear force. Because of this, they pass through ordinary matter almost completely undisturbed, making them incredibly hard to detect. Yet, they are among the most abundant particles in the universe. In the first few seconds after the Big Bang, neutrinos were in thermal equilibrium with other particles, exchanging energy rapidly. However, as the universe expanded and cooled, these interactions became increasingly rare. At around 1 second after the Big Bang, neutrinos decoupled, meaning they stopped interacting significantly with other matter, and began to travel freely through space. This moment left behind a sea of relic neutrinos, known as the cosmic neutrino background (CFB), analogous to the better-known cosmic microwave background (CMB), but formed even earlier. While the CFB has not yet been directly detected, its existence is strongly supported by theoretical models, and its indirect effects are measurable. For instance, the number of neutrino species affects the expansion rate of the universe during the first few minutes, which in turn impacts the outcome of primordial nucleosynthesis. Observations of element abundances and the CMB suggest that there are 3 active types of neutrinos, consistent with predictions from the standard model of particle physics. Moreover, neutrinos contribute to the total energy density of the early universe. This energy density plays a critical role in determining how quickly the universe expands, how long nucleosynthesis lasts, and thus how much of each element is formed. In summary, although neutrinos are almost invisible, they are key players in shaping the universe's evolution, helping to maintain energy balance and influence the delicate timing of element formation. What happened after the first 3 minutes? At the end of the first 3 minutes, the universe had cooled to below 1 billion degrees Kelvin. This marked a turning point, a shift from a universe dominated by extreme nuclear reactions to one in which nuclear fusion could no longer occur efficiently. From this point forward, no new atomic nuclei were formed in significant quantities. The conditions were simply no longer hot or dense enough to overcome the electromagnetic repulsion between positively charged nuclei. This freeze-out effectively ended the process of Big Bang nucleosynthesis. So, what was left behind? Roughly 75% hydrogen, mostly in the form of protons H1, and 25% helium-4, with trace amounts of deuterium, helium-3, and lithium-7. These abundances remain consistent across the observable universe, serving as powerful evidence for the accuracy of Big Bang models. With no more nuclear fusion taking place, the universe entered a quiet but critical phase. The matter was still ionized, meaning electrons, and nuclei had not yet combined into neutral atoms, and photons light constantly scattered off. Free electrons. This made the universe opaque, like a dense fog. This foggy state persisted for hundreds of thousands of years. During this time, the universe continued expanding and cooling slowly. Radiation began to decouple from matter, paving the way for the next major milestone: the formation of neutral atoms. This era is often called the Dark Ages of the universe. There was no visible light, no stars, no galaxies, just a cooling soup of hydrogen and helium ions, free electrons, and background radiation. This calm, invisible stage would last until about 380,000 years after the Big Bang, when electrons and nuclei would finally combine to form stable atoms in a process known as recombination. Only then would the first light travel freely across the universe, creating the cosmic microwave background, the baby photo of the cosmos. But all of it came after these first 3 minutes. In this brief window of time, the fundamental ingredients of matter were forged: the protons, neutrons, and light nuclei that would eventually build everything from stars to planets to life itself. The meaning of the first 3 minutes in just 3 minutes. The universe laid the foundation for everything we know today, from the seething chaos of quark-gluon plasma, to the birth of stable protons and neutrons, and finally to the formation of light nuclei. These early moments shaped the chemical blueprint of the cosmos. It is astonishing to realize that nearly all the hydrogen and helium in your body, in the oceans, in the stars, were formed within this narrow slice of cosmic time. No stars had yet lit up. No galaxies had yet spun, but the seeds of all matter were already sown. Big Bang nucleosynthesis not only explains the abundance of light elements, but it also confirms a critical aspect of cosmology, that the early universe was hot, dense, and expanding rapidly. The precise predictions it makes have been confirmed by satellite data and ground-based telescopes for decades. Moreover, the balance between protons and neutrons, determined by the weak force and the temperature at that time, ultimately set the stage for all nuclear reactions to follow, from the fusion inside stars to the supernovae that would later create heavier elements. This moment was the transition from chaos to structure, from randomness to rule-based physics. It shows how even in extreme conditions, the laws of nature operated with remarkable consistency, and from them emerge order, complexity, and eventually, life. We often think of the Big Bang as a single explosion, but in reality, it was a carefully choreographed unfolding of events governed by fundamental forces. These 3 minutes were not just the universe as beginning. They were its first great act of creation. What do you think about the idea that everything in the universe, from the air we breathe to the stars we see, was born from a nuclear soup that existed for just 3 minutes? This brief period, though long gone, still leaves its signature in every atom around us. And understanding it helps us grasp not just how the universe began, but how we came to be. If this journey back in time sparked your curiosity, imagine what's next. Because in the next episode, we'll travel to the moment when light first appeared in the cosmos, the era of recombination, when atoms became neutral and photons finally broke free, giving rise to the cosmic microwave background. That light is still traveling through the universe today, carrying messages from 13.8 billion years ago, and we now have the tools to decode it. So if you want to continue this exploration with us, make sure to subscribe to the channel, like this video if you learned something new, and share it with friends who are curious about the universe just like you. And don't forget to leave a comment. What surprises you most about the universe? As first 3 minutes, we'll see you in the next video, where darkness ends and cosmic light begins.